Okay, so this is the time we should start. Let me go and mute everyone first. Okay. Good afternoon and good evening, ladies and gentlemen. We are immensely pleased to have Professor David Sherrill with us. And this is he's going to talk about a very important topic. But let me give you the brief. And another thing is, I will mute everyone during the lecture. And if you have any question, you can go to the participants and raise your hand. I will call by name, the first come, first serve basis. I'll call the first one. And then if still you are unable to do it, you can put your question in your name in the chat. But I'll prefer you raise your hand and I will go one by one quickly at the end of the lecture. Lecture is being recorded, so it will be available in our department website, or we will let you know where it is being placed. But we are going to record this lecture. It's a short introduction. Well, if you look at the CV, I was just reviewing it. It is 34 pages, by the way, Professor Sherrill. I downloaded it from your website, but it's too much. I cannot read all. I am just going to summarize few highlights. Professor David Sherrill, he did his BS in chemistry from MIT, PhD from University of Georgia. He is a professor at the School of Chemistry, and you can see School of Chemistry and Biochemistry, School of Computational Science and Engineering, Georgia Tech or Georgia Institute of Technology. And if I need to talk about his honors and awards, these are the countless. I cannot, mention even one. The last one is College of Sciences. He received the award for the faculty mentor. More than 24,000 citations. I think what I was saying is it was close to 25,000 citations he has, with H index of 74, and he published more than 200 papers, articles in scientific journals. He also published 9 book chapters, and he had numerous funded projects as a principal investigator and co-investigator. Courses, he also taught the graduate courses, quantum mechanics or quantum chemistry and molecular spectroscopy, but he is also teaching general chemistry, which is, I believe, freshman chemistry. This is the thing which we want to share actually. A professor of such eminence is teaching the freshman chemistry there. Well, with this, I would like to give mic to Dr. Sherrill, and he will take us to end of his presentation. And again, I remind you, if you have any question, please raise your hand and go to the participant list and you can raise your hand. Mic is yours, Professor Sherrill, and you may continue.
Thank you very much, Dr. Siddiqui, for that kind introduction. It's a pleasure to be with you. Good evening, everyone. I'll tell you a little bit about some of our recent work in applying machine learning techniques to intermolecular interactions. And I suppose you're all aware that machine learning has become an important new topic in chemistry over just the last few years. So the intermolecular interactions that I'm going to tell you about, let me try to explain what I mean by that. I just mean the interactions between a pair of molecules. So, you know, you could have hydrogen bonding or various kinds of interactions. We can model those quite accurately now with quantum chemistry, but frequently those calculations take a lot of computer time. And so our goal is to try to find a quicker way to do those calculations, maybe with the aid of machine learning. So my primary target is the energy of interaction between these two molecules, which I can define very simply as an interaction energy just being the energy of the dimer minus the sum of the monomer energies. So nothing very fancy, although I'll make it slightly fancier here in a second. So there's monomer A, whatever it is, there's monomer B, and the dimer is just the union of those. Okay, Now, here's where I make it just a tiny bit fancier. The way we're going to start off is by using quantum mechanics, and we're going to use something called symmetry adapted perturbation theory. And what this is, it uses the normal techniques of quantum mechanics and perturbation theory, but applied to the problem of interacting electron densities. And essentially what you do is you do Hartree-Fock molecular orbital calculations on monomer A and then on monomer B, and then you use perturbation theory to see how they interact with each other. And a lot of terms fall out, and I won't go over all the details of the terms, but I will make the point that the terms have a natural physical interpretation. So you see that there's one term that describes the electrostatic interaction between these two, one that describes the exchange repulsion, one that describes dispersion, and they all have these nice labels. And I'll remind you what those terms mean in a second if you've forgotten. So I combine them just into an electrostatic term, an exchange term, an induction term, and a dispersion term, and those have a physical interpretability that we can use. Okay, so what do those mean? If you haven't taught freshman chem for a while, you might have forgotten what some of those terms mean, so I'll remind you quickly in one slide. Electrostatic interactions are just things like charge-charge, charge-dipole, dipole-dipole. All of those kind of interactions are electrostatics. London dispersion forces are when I have an instantaneous dipole moment that induces a complementary dipole moment, and so those interactions are weak, but they're always present. I have induction, or sometimes called polarization terms, if a dipole induces a complementary dipole. And then finally, I just have short range exchange repulsion due to the Pauli principle. So those are the 4 forces that I'm going to worry about. And just one slide to try to convince you that the symmetry adapted perturbation theory is a very useful approach. Many years ago, I had an undergraduate visit my lab and work with me for the summer. And I asked him to study the interaction of cations like sodium cation or lithium cation with benzenes. And I was curious about the physics of these interactions. And he used this symmetry adapted perturbation theory to calculate interaction potentials if I change the distance between these. And the total energy is in black. And you see that it's 0 at long range, of course. And then at short range, it's a little bit attractive. So this is below 0. Interaction energies below 0 are attractive. And then eventually it gets positive if they get too close, of course. And so you might ask, well, why could this be attractive? Because if I have a cation, it probably should be repelled by the hydrogens, because the hydrogens in a benzene will have a partial positive charge. But it turns out, if I do the symmetry adapted perturbation theory, I get all these components that I just mentioned on the previous slide. And you see that electrostatics, which would be charge-charge, is repulsive, just like we would expect. But it's not the only term. If I look at this induction or polarization term, I see it's very attractive. And what that is the cation pulls electron density towards it and creates an induced dipole. So I have a charge-induced dipole interaction, which is very strong, and it overcomes the electrostatic repulsion so that the entire interaction is favorable. So I really like this SAPT approach because it is quite accurate, and it also allows you to understand the interactions in a deeper way. But the problem is the calculations take a long time. So we want to find a way around that. Just quickly, one more example of SAPT in a maybe more useful application. We teamed up with Bristol Myers Squibb, the pharmaceutical company, to apply SAPT to better understand the difference between different drugs they had and their ability to bind to this protein, which is called factor 10A. And this is a protein that's relevant in blood clotting. So they had various drugs, and the drugs often have 2 groups that are aromatic, S1 and S4. Those refer to the binding pockets in the protein. And they said, you know, the S1 binding domain often has an aromatic, and it can either have a chlorine or a methyl group. And they said, you know, it seems like the chlorine works better than the methyl, but we don't understand why. So we did these SAPT calculations, and I'm showing you some color-coded maps. The ligand, the drug, is in deep red, and then the protein, I've shown you just a piece of it around it. And we color-coded the protein so that the red parts are very attracted to the drug, and any blue parts, there's not very many, are repelled by the drug, and we could kind of see where the binding was good. And on the left, I'm showing chlorine on the drug, and on the right, I've replaced the chlorine with methyl because we're trying to understand why the chlorine binds better. And these two pictures really look about the same, so it's a little hard to tell any difference. We subtracted the two to create this picture, and in this picture, you see that there are some red pieces where the protein likes the chlorine on the drug better, and there are some blue pieces where the protein would prefer the methyl. And you see it's a sum of positive and negative contributions, and there are ultimately more red contributions, meaning the chlorine is overall more favored. But it's kind of a complicated story. There's not just one piece of the protein that's relevant. There are many, many parts. And in fact, it's the peptide bonds in the protein. And it turns out if you replace the chlorine with a methyl, you change the local dipole moment on the drug. And that change to dipole has different interactions with different dipole moments on the drug. And so that was a really interesting investigation. But again, the calculations were very time consuming. We did use our program, Sci4. I'll mention it very briefly because some of you might want to try it if you ever want to do some quantum chemistry calculations. We have an international collaboration of developers who writes the software. It's free and open source. Anyone can download it, and it can do SAPT calculations or molecular orbital calculations or DFT calculations. It has a lot of nice features. Okay, so now with that as background, let me dive into the details of the project. What we want to do is create a machine learning model that is almost as accurate as symmetry adapted perturbation theory, but that would be much, much faster for the calculations. And this is a little tricky. You might say there are a lot of papers now on applying machine learning in chemistry, and there are. Almost all of those deal with the total energy of a molecule, but not the attraction between two molecules. And it turns out that's a very different problem because that interaction energy is a difference between two very large energies of the monomers. And so you need really good error cancellation to get an interaction energy. And that's not something people have focused on in machine learning and chemistry before our work. Some of the common approaches in machine learning may or may not apply. I'll indicate that as we go forward. And there's really no pure machine learning model of these fundamental forces like electrostatics, dispersion, exchange, or induction. So let me say a little bit about machine learning and neural networks. I won't get into a whole lot of details, and honestly, my graduate students know more about this than I do. It's a kind of a new field for all of us. But we started off with these neural network approaches pioneered by Baylor and Paranello, where you have some kind of mathematical descriptors or mathematical information. You could think of it as a bunch of different functions or a vector of numbers. And this goes into the neural network. The neural network then feeds information across from the left to the right, where each node of the neural network has access to the input data that you provided, and it weights this information with different weighting factors that are learned during the training of the neural network. And then this goes forward for 2 or 3 or 4 or 5 layers until you finally get an output. And the traditional way to do this is to have one neural network per atom type. So there's a hydrogen network, a nitrogen network, a carbon network, etc. So that's where we started our work. And you do this for all the different atoms in your system. All the hydrogens go through the hydrogen network, et cetera, and you get out either an energy or some kind of property, and then you sum those up to get the total molecular property. Now, what we're going to do is try what Baylor and Parnello introduced as atom-centered symmetry functions, ACSFs. And this is a mathematical function that basically looks at an atom I, and it sees what are the nearby atoms, and then it takes the atomic number for each nearby atom J, multiplies it by an exponential that depends on the distance between me and all the other atoms. And then this FC is just a cutoff function that eliminates very long range interactions to speed up the calculation. There's also an angular version of this that I won't go over, but it involves triples of atoms. So these are slightly complicated functions, but they're not all that hard to compute. And that gives me essentially an idea of the local chemical environment around every atom I. And that's the information I pass into the neural network. These have some certain mathematical properties that are good to have. I'll gloss over that in the interest of time. And we applied this approach to a bunch of hydrogen bonding systems. In February in 2020, our paper came out in Journal of Chemical Physics, and that's part of a special issue that is just closed, I think, probably in JCP. All right, now how did we train the model? In machine learning, you have to have a lot of data, and you feed it into the model and you train the model. So how do we do that? Well, the first thing we did was a very, very simple experiment. Instead of looking at many hydrogen bonded interactions, we just looked at one, okay? So we looked at this molecule N-methylacetamide, and then we interacted it with a methanol, and then we just put the methanol in different locations. And for each location, we computed a symmetry adapted perturbation theory energy. And that's a quantum mechanics calculation, so it's expensive, but these are very tiny molecules. So we can do many of those calculations without any problem. And so here's what we tried. We looked at 8,000 different geometries, like I just showed you on the previous slide. We used symmetry adapted perturbation theory. And we just kept the monomers rigid and just put them in different locations. Then we made another 1,000 geometries just to test the predictions. And then as a better test, we took out 40 crystal structures of N-methylacetamide interacting with, oh, I guess these are anilines in this case. I think I showed a methanol in the previous slide, but same idea. Aniline in this case, to just independently check if the model was accurate or not accurate. And here's the results. So I'm showing you correlation plots where these are those 40 independent crystal structure tests. And on the x-axis is the symmetry adapted perturbation theory computation, which should be accurate. And on the y-axis is the neural network prediction. And you can see that there is a correlation. I've got dotted lines plus or minus 1 kilocalorie per mole. It's not very impressive, okay? The calculations are cheap, but we were hoping for better results than this. We got a mean absolute error of 2 kilocalories, which is maybe not terrible, but we really wanted something better. If I look at the energy components, electrostatics, exchange, induction, and dispersion, some of them are better. The dispersion is predicted very accurately. Mean absolute error of 0.18 kilocalories per mole is not bad at all. But the sum is not very impressive. So I wanted to tell you about our failure here because I think that taught us more than some of our successes. We wondered what went wrong. Did we not have enough data? Maybe we needed, 20,000 training points. Did we have the wrong kind of data? Did our way to encode the data go wrong? That's called the descriptor. It turned out after thinking about it for a few days, we realized we really had the wrong kind of data. What we did seemed to make sense at the time. We had one molecule and then we scanned another molecule around it in different geometries. But the problem is we fixed the monomer coordinates as being completely rigid. So we had fixed bond lengths and fixed bond angles. And if you think about it, if you then train a model this way, but then you try to predict on crystal structure geometries, the crystal structure geometries, of course, will have slightly different CO bond lengths or bond angles than we used in our theoretical training. And what will the machine do when you give it monomer geometries that are a little different? Maybe this bond is, 0.001 angstroms larger. Well, we as chemists would know that a very tiny change in bond lengths or bond angles shouldn't affect the intermolecular interaction. But that's us as humans. The machine doesn't know that. And so that's why the machine learning predictions were poor. We were giving it different kinds of situations to predict, even though to us they seemed the same. And the machine gave us not very good predictions because of that. So how can we fix this? Well, I asked the students to just perturb the Cartesian coordinates of all their training data and just shift the bond lengths and bond angles a little bit by random amounts for each of our 8,000 training configurations, and then regenerate the interaction energy and teach the machine learning model about that. So now it's the same procedure, but I've got perturbed atomic coordinates just to give a bunch of slightly different bond lengths and bond angles. And now I get a greatly improved result. So my mean absolute error went from almost 2 kilocalories per mole down to almost a half a kilocalorie per mole. So this was a big, big, big improvement. Many of the points are now within plus or minus 1 kilocalorie for our testing data of the crystallographic geometries. And the components all look quite good as well. So we were very pleased with this as a kind of a proof of concept. Now, this was only hydrogen bonding interactions, okay? And we're really more interested in general models, but we thought this was very, very promising. I think I'm going to skip this slide. Is a little bit technical. Don't need that right now. Well, I'll try to mention it very briefly. We decided it was important in these so-called symmetry functions to distinguish between intramolecular coordinates, where I look at neighbors that are in the same monomer as me, versus intermolecular coordinates, where I look at atoms that are in a different monomer than me. And we felt that that was important to be able to give the machine learning model additional information. So we did that tweak, and then we reduced the mean absolute error from 0.62 down to 0.47. So that was another minor improvement. Okay, we really wanted to have a more general model. So that model I just told you about actually was only for a single hydrogen bonded donor and acceptor, which is not particularly useful. So then using those approaches, we looked at 53 hydrogen bonding sites and 96 hydrogen bonding acceptor sites and came up with 2,000 neutral amino acid pairs from a data set we created in 2017. And then for each of these different hydrogen bonding donors or acceptors X, we interacted that with N-methylacetamide and picked different random geometries of the different distances and angles in about 20 to 90 each of those 149 complexes. So that gives us 6,400 training data. And then we picked out 1,000 or so validation data to tune our parameters. And then as a completely independent test, we looked at another 2,200 molecules. One of the things we decided to do also was ask the question, what are we trying to learn? Originally, we were talking about learning the interaction energy, but remember, I have different kinds of interaction energies going on. I have a total interaction energy, but I also have these different components. I have my electrostatics, exchange repulsion, induction or polarization, and London dispersion, and then these add to the total interaction energy. So we asked the question, is it better to train these 4 components independently and then simply add them, or should our training procedure have some kind of weighted average where we try to get these 4 right, but also get the total interaction energy right? And we tested that here in this graph. So what I'm doing is I have a so-called loss function. It's just an error function. I'm tuning it with this parameter gamma. I'm saying I could look at the mean signed error of the interaction energy, which is the sum of all the components, or I could look at the sum of the errors of the individual components, and I could change the weighting factor. So let's see, if gamma is 1, this term goes away, and my error function is only the sum of the components. Or if gamma is 0, I don't look at the components and I look at the total interaction energy. And you see, if I pick about 0.4 for gamma, the total interaction energy error is quite low, and it never really gets much lower than this. But at 0.4, the components are also pretty low as well. So I get good errors on all the components and the total. So we picked 0.4. So with that multi-target loss function, here's the results for this much bigger challenge of hydrogen bonding. You see I have many points here. So this is my, how many did I have? I forgot. 2,200 test data. So there are 2,200 points in this graph. It's not surprising some of them are a little off, but a lot of them are plus or minus 1 kilocalorie, which we're very pleased with. Mean absolute error of 1 kilocalorie per mole. It's not fantastic, but not too bad for such a large data set. And the components look pretty good as well. They have mean absolute errors of either about 1 kcal or just a fraction of a kcal. And I apologize, there's a little noise outside, but I can't control that. All right. A couple of the data points are very poor. We looked at those and said, what's going wrong with these? These are cases where the crystal structures had very close contacts. And we kind of wonder if those crystal structures are entirely accurate because the contacts are so close. Okay, so that all made us very happy that we seemed to show we could use machine learning to predict hydrogen bonding energies with a pretty good accuracy. And these machine learning computations are very fast. They just take seconds. So what we're doing now is trying to use much larger training sets and go after general interactions between organic molecules, not just hydrogen bonding. Another thing we're doing is we've switched how the neural network works. And let me see if I can explain that, because we've had good success with this switch. One of the things I asked the students to do, which we didn't do in the original paper, was look at how smooth the potential energy curve might be or not. So our symmetry adapted perturbation theory is in black, and this is my picture got cut off. This is a water dimer. Of course, the quantum mechanics gives me a smooth potential. But notice the machine learning model based on SAPT gives me this very jagged curve. It's not very nice. In fact, if you wanted to do some molecular dynamics simulation with this, you could have a lot of trouble. So we realized we needed to do something better. The setup really was wrong. What we were doing, and what everyone does in machine learning and chemistry, is they always say whatever property you have is a sum of atomic contributions. And for our interaction energy, each atom in monomer A contributes by how much it's attracted to monomer B, and each atom in B contributes by how much it's attracted to monomer A. The problem with learning this, even though it kind of worked for hydrogen bonding, is that what you're ultimately doing is trying to teach a machine how a given atom with a certain electronic environment interacts with any kind of other molecule. And because there are an infinite number of molecules, this is very, very hard. What we switch to instead in our new work is not to predict atomic contributions, but to predict atomic pairwise contributions. And in fact, this is how most force fields work. So here you say, I've got a particular atom A in monomer A and a particular atom B in monomer B. And how do those two atoms interact? And in chemistry, there are only a finite number of different possible local environments of monomer of atom A or B. You might have a sp3 carbon, you might have an sp2 carbon, it might have, you know, different kinds of neighbors nearby it, but there, in organic chemistry at least, there's just a finite number of possibilities for what's around an atom. So this should be easier to learn. So to try to illustrate this graphically, the old model looked at each red atom in this monomer with the entirety of the other monomer and vice versa. And there are too many possible other molecules. Now we're just saying for this particular atomic environment, how does it interact with all these other atomic environments? And that's much easier for a machine to learn. All right, so the new model, APNet, we're calling it Atom Pairwise Network, gives me this red curve, which is nice and smooth. It's not super accurate, and we need to work on that, but that's because this is initially trained on those same hydrogen bonding systems, and I'm applying it to water dimer, which is a hydrogen bonding interaction, but water dimer was not in any of my training data. In fact, waters weren't in my training data. And so the results would be much better with more training data, but we're very, very pleased that the potential is now smooth. All right, so how accurate was this for the same hydrogen bonding test set I showed you a minute ago? The accuracy is improved. The mean absolute error is now reduced to 0.37 kilocalories per mole, so it's pretty good. All the components look good and the total looks good. There are a few outliers, you know, that's inevitable with machine learning models, but we think this performance is very nice. So let me just, in the last few minutes, give you a little preview of some current work that we haven't published yet, where we're trying to take this APNet idea, but now look at data sets that are much bigger than just hydrogen bonding. So we've initially trained it on 100,000 SAPT energies, which is a lot of energy. So it's a good thing we specialize in doing lots and lots of quantum mechanics calculations. What we've done is taken, made a list of many, many organic molecules, and we interact each of our organic molecules with either our other organic molecules. And the grid picture is just meant to denote that I look at all possible pairs. So like this chlorobenzene with this methyl chloride, for example. And of course, there are not enough possibilities here. So those aren't the real ones. But for each pair, I then do a monomer scan like we talked about a minute ago, where I put one monomer fixed, the other one I move at different distances and angles, and then I perturb those interatomic coordinates. This is more like the real list. These are too small for you to see. I know I'm just trying to convey there are many, many molecules that we're studying in our training set. All right, so preliminary results. This is a methylamine dimer, and I'm again checking for if I get smooth curves. So our results are on the right. APNet is the red curve. It's very, very nice. And the SAPT0 that it's trained against is in black, and there's a very nice agreement. So we're pleased with this. A competitor might be this Annie-1 approach of Adrian Reutberg from the University of Florida. His approach is not meant specifically for intermolecular interactions, but it can do them. He trained against a different level of quantum mechanics. So to be fair, I'll compare his method to his benchmark method, which is a density functional approach, omega B97X. And you can see that the agreement is not very good. So we're not very optimistic about this particular model, and we think APNet is doing better. One more example, ethylene with pentane. Again, we get good agreement. The literature models are not doing very well. So let me wrap up in the next few minutes by just giving you some examples of larger systems, because that's the real goal. So this is rather larger. It's not as large as we really want to get, but here's a 159 atom piece of this factor 10A protein I mentioned a while ago, interacting with a particular ligand. And here is a SAPT0 calculation. So we can do this calculation. It takes quite a few hours, but we can. And here's the total interaction energy in black and the different components I've been talking about in different colors. And then here is the APNet prediction based on our preliminary model with 100,000 training data. And the agreement looks very, very good. So we're pleased with that. Let's do an example like we did with our Bristol-Myers Squibb collaborators. Let's say, what happens if I take a methyl and replace it with a chlorine and predict how that increases or decreases the binding with the protein pocket. So here are fragments from 10 different crystal structures. And I can do the SAPT0 calculations and say what's the difference in interaction energy between methyl and chlorine. And I get these different numbers. And then here's a prediction with our machine learning model. And there's not perfect agreement. So this predicts 0.38 kilocalories. This is 1.33 kilocalories. So it's not perfect, but they have the same sign. And we get the same sign in 9 out of 10 cases. This is the one where we get a different sign. So if you wanted to rapidly screen drug candidates or, you know, test different perturbations, then it seems like the machine learning model should be perfectly good for that kind of application. Now, how fast is this? So these 20 SAP calculations took 8 days of computer time, 9 hours each. All 20 of the neural network calculations on my graduate student's laptop took 5 seconds. So that's the improvement that we're getting. We can do color-coded maps of components of the energies like electrostatics. So this tells you what pieces of the drug are very attracted to the protein. The chlorine is very, very attracted. The sulfur is, this carbon. And then what pieces of the protein are very attracted to the drug, this oxygen, this hydrogen, and so forth. So that's useful. And then here is a big system. I think this is 2,200 atoms, if I remember right. And we can do this calculation. So the drug is a little hard to see. The drug is in here somewhere. It's interacting with the protein, and we can color code where the interactions are good in red and where they might be poor in blue. And this whole calculation, if I remember correctly, again, took about 20 seconds with the machine learning model. So, and we could never do quantum mechanics on this. It would just be too impossible. Okay, so let me wrap up so we have plenty of time for questions and comments. I hope I've convinced you that it looks promising that machine learning might really be able to give you almost quantum mechanical accuracy at a much reduced computational cost. The calculations go from hours or days down to seconds. However, it's hard. So you have to pick your training data very carefully, and you have to encode it in a very carefully selected way because the machine isn't actually smart. Sometimes they call this artificial intelligence. I like machine learning better because artificial intelligence makes it sound like the machine is smart, but it's really not. So we have to teach it all the details that are relevant. And finally, this has been really fun to work at kind of the intersection between chemistry and computer science. And that's been really enjoyable for me and the students. One preview slide of a paper we hope to submit in the next few days. We also now have a machine learning model to predict atomic charges or atomic dipoles. In this particular slide, I'm just giving you a demonstration of that. I'm plotting the charge on a carbon atom. I forget which one of the carbon atoms. This is aspirin molecule. And for people who do molecular dynamics, what they would normally do is calculate the charges on the atoms using quantum mechanics and then fix them for the entire simulation. But what we've done is we've actually recalculated them at each point in a molecular dynamics trajectory. And those are, which ones are those? In BIS, we used a technique called minimal basis iterative Stockholder. Doesn't really matter, technical. But the red curve is the quantum mechanical charge. It changes a lot. It goes from 0.55 down to 0.40. That's a large change in a charge on an atom. And we have a neural network now that can predict these changes in the charge. And that's the blue curve. And you can see that it does a pretty good job of mimicking the red curve. So we hope that maybe in the future, people could do molecular dynamic simulations with dynamic charges, thanks to neural networks. Okay, so let me just thank the students who did all the hard work. A lot of the work I told you about was due to a fellow named Derek Metcalf. So he's in this bottom picture in the purple t-shirt. Some of the work on that very last slide, for example, and on APNet was due to a graduate student named Zach Glick. And I think Zach joined us recently enough, he's not in these older photos. And I didn't have time to talk about it, but a lot of fantastic work, not in the machine learning part, but in molecular dynamics simulations in the group, has been done by Asim Alnazan, who I understand is a graduate of your university. He's been a PhD student with me now for a while, and he's doing fantastic work. We just got a paper of his review comments back from Chemistry European Journal, and it sounds like the reviewers really like it. And so we're looking forward to revising that and getting it out. But Asim has been doing really nice work on a lot of molecular dynamics simulations of different self-assembled systems, working with some collaborators at Georgia Tech and also Scripps. So with that, I will also thank all of you for your kind attention, and I would be very happy to answer any questions.
Thank you very much, Professor Sherrill. It was wonderful talk, very well received, and I'm sure there'll be some questions. And the first question is from our colleague, but let me make it clear. I mean, we please ask one question, and if you have another question, you may have it the follow-up question. Then we will wait for other people to ask the question if they are. Otherwise, we will see. So our first question is from Dr. Janjua. Dr. Janjua, you can unmute yourself.
Yes, thank you very much. Can you hear me, sir?
Yes.
Yeah, thank you, Professor Sherrill. It was a really very nice presentation, and I have learned many things. In this, I'm Muhammad Janjua from Physical Chemistry Division, from Chemistry Department. And for several years, I have been working with density function theory calculations. So actually, I have two questions, but as my host told me that I can ask only one question. So I will ask only one question. If I found more time, I will ask the second question. But my question is this, that regarding the counter ions, because as I told you, for several years, I have been working on DFT and TD-DFT calculations. For example, there is one species having charge -2, but in real time, it cannot exist. We know that. So there should be some counter ion. But when I'm going to model that species, usually I do not consider the counter ion because, as you know, that it has weak electrostatic interaction. So is there any, participation of these counter ions there? I mean, can we model the molecules by using SAPT? Because my response for this question for all the referees every time, very simple. It is a counter ion, it has weak electrostatic interaction, so it does not matter. But now in this era, we cannot say, because in computational chemistry, we should consider that counter ion. So this is my question. And related to this question, as far as you told me about SAPT, so can we also model frontier molecular orbitals by using SAPT? And if yes or no, in both cases, how SAPT is different from Gaussian and ADF softwares, which are, DFT-based softwares? Yes, thank you.
Okay, great questions. Let me answer the bit about SAPT quickly first. SAPT is part of our Sci4 software, so if you download that, you can try it out. It does have one very important limitation. SAPT, it only works for 2 molecules because it assumes monomer A and monomer B. So if you have a complex system where you have a lot of water molecules and counterions, you can't really apply SAPT unless you group the entire environment together in one monomer. And then you could, but then the calculation will be too hard. So it's great, but really only for systems about 400 atoms or less, and only can do things with one group and then the second group. You asked about counterions and are they important? Can we model them? Yeah, I agree with what you said. I think as we go forward, now that we're in 2020 and we're trying to be more accurate and more serious in our modeling, I think it is important to try to include the counterions whenever we can. And that's one reason I really like this machine learning approach, is that it's fast enough. You could include the entire protein and all the solvent and all the counterions, and that would be feasible. Whereas with something like DFT or SAPT, the system is just too large, so it would be impossible.
Okay. And
okay, thank you very much. Dr. Jeju, you may ask later. Let me go to the next question. Dr. Musa, you can unmute yourself. Dr. Jeju, you can mute it, please. Yes, Dr. Musa.
Yes, this is Dr. Musa from Chemistry Department. Thanks for this great presentation. Till now, from what I see, that it's really tough to do, this protein engineering guided by combination of molecular mechanics and, it's not easy to get the guidance still properly. So do you see us doing directed evolution, for example, based on machine learning or protein engineering, of course, guided? We don't need directed evolution in this case. It will be protein engineering directed by machine learning. So do you see that directed evolution is not needed 5-10 years from now, let's say?
Interesting question. I have to admit I don't really know anything about directed evolution, so I can't say a lot. It sounds complicated, but what I can say is that, a lot of times people have asked biological questions and tried to use force fields and molecular dynamics, and sometimes that has been helpful and other times it hasn't been so helpful. And in my opinion, the times it's not helpful are either that really modeling the process is still too hard, even for molecular dynamics, or the molecular dynamics hasn't been accurate enough. And I'm not sure if we can make these machine learning models like the ones I talked about fast enough to replace molecular dynamics. They're really about the same computational cost. But what I do hope is that we can make the molecular dynamics and force field models more accurate than they are now. And so maybe this will give us a way to answer some of the questions we couldn't answer before, because now we'll have a boost in accuracy.
Okay, thank you very much. There was Saleh before, but I do not see his hand now. Saleh, iPhone, he's not here. Okay, next is Almaz. You can unmute yourself.
Hi, Dr. Sherrill. This is Almaz from Chemistry Department. I have a question related to this, the work that you just presented with this, I think it's acetamide with the methanol where you started. In the beginning, when you introduced machine learning, you were around 2 kilocalories accuracy off from the target. But then when you introduce the flexibility of the methanol, and then you go within the 1 kilocalories. But if you look at the graphs, in particularly in dispersion interaction, and then I think it's induction interaction, it does not really change the accuracy for those 2 particular interactions. The main change were in electrostatic part. So that left me with an idea that it is slightly sensitive toward one interaction over the other one, and it is more selective, let's say, toward electrostatic interaction versus the other two interactions. And this that's what it left me with the feeling. Don't you think there is some missing part with regard to the information that's given from that particular dispersion and then induction interactions?
That's very observant of you. I agree with all of your observations about my graphs. That's correct. The when we perturbed or didn't perturb, things like dispersion didn't really change, whereas the electrostatics changed a lot. The mean absolute error there went from about whatever it was, 1 point something to about 0.5 kilocalories. So that's true. And why might that be? Well, apparently, the electrostatics are more sensitive to bond lengths and bond angles, whereas apparently dispersion isn't. I think largely this has to do with the fact that the electrostatic interactions are just much larger. The range on the electrostatics was about twice the range on, say, the dispersion terms, and so my interpretation is it's just a consequence of the electrostatic interaction being a bigger interaction, and so therefore it has more variation. There might be something more subtle to it as well, but I'm not sure.
Is there any way, so to say, to analyze the dispersion interaction in compared to the electrostatic interaction? Just saying that electrostatic interactions are more important than dispersion, I think it is slightly will be misleading if you agree with me. But I think dispersion and other interactions would be as important as electrostatics. I think I think it's open question. But do you think you can, for example, the machine learning can be taught for the dispersion interactions to analyze those as good as electrostatic interactions, so we can have exact numbers that we can sort of compare them?
Well, yeah, I'll go back to the slide you're talking about. We get very good, let's see, which one is that? You were talking about the original one, so I'll go back to that. This one. So this was after we perturbed the geometries. We get really great results for the dispersion. We're down to a mean absolute error of 0.12 kcal per mole. So and we see this for our later models. So when we have the more general model with APNet, it's also very, very, very accurate for dispersion. So that one, I'm quite optimistic that the machine learning model can just do a fabulous job on dispersion. It's true in our more recent models, electrostatics is still a little harder. So here it's 0.47, exchange is 0.46 here. These qualitative trends remain true for the APNet model, that dispersion, the machine can get almost perfectly. Induction, it can do a pretty good job. And then it's harder to get electrostatics in exchange for some reason.
Right.
Thank you, Almaz. Thank you. Now, next is Dr. Saleh Al-Arfaji. Can you unmute yourself, please, Dr. Saleh?
Assalamu alaikum. Thank you, Dr. Siddiqui. And thanks, Prof. Sherrill. It's very lovely and very nice talk. I really appreciate it. And I wish that I am at a good signal area. But anyway, I just try my best to follow your talk. And I have a very general question about the machine learning algorithms that you have used here. As I know that there are tons of the algorithms that you can use, but I'm not sure about what is the main purpose to use the neural network in this time. And have you tried any different algorithms beside this kind of algorithms or not? The second question, sorry about that, just to ask you about the SAPT 0, because I have tried the Psi4 a couple of times. But I'm not sure. But I'm not sure to which limit that you are going to think in the future. Can you extend the work besides just only working on the monomers right now? for trimers or whatever, so, or a kind of a complex system, a little bit, including or excluding the water molecules, as you know, because it's very lovely, type of codes that I really like, and it's very fast, and really like that. And thanks.
Excellent. Okay, so let me, I'll try to answer both of those parts quickly. The first part, we really have looked almost exclusively at neural networks. As you mentioned, there are other things. There's random forest models, there's a lot of things. There's kernel ridge regression. We like the neural networks because the time it takes for the neural network to make a prediction is linear in the amount of information you feed it. So that contrasts to some of these kernel ridge regression methods where you might have to do a lot of lookup information. What did I say, linear? I don't want to mean linear. Let me restate what I said. The neural network prediction is basically a constant time prediction. Whereas if you do KRR methods, you have to do a comparison against every member of your training data. So there it's linear in the amount of training data, which is terrible. So if I have 1 million data points to train a KRR model, my prediction time is terrible because I have to go compare it to all 1 million of my training points. So that's one advantage of the neural networks, is that they're fast and they remain fast no matter how much data you dump into them. Your second question about the SAPT, yes, it is a limitation that it only does, dimers. I'm working on a paper right now in my spare time that I'm trying to look at what happens with SAPT if you do try to take a look at complex systems with many water molecules, and how would you think about that? How would you model a many component system? And it looks like that apart from the induction or polarization term, everything really is kind of two-body interactions. And that induction term is not large usually. So I think you could do some kind of mini body expansion with the two-body SAPT and still get reasonable results even for complex systems. And I hope to submit a paper before too long that kind of makes that point.
Thank you very much, Dr. Salih, for your question. Dr. Sherrill, I have one question before I go to the Dr. Janjua again. So, they put in the chat, and what he's saying, my question is, how many layers of neuron did you use in your work and each layer's function? And what is the function of each layer?
Okay, yes. My students remember better than me how many layers. You don't have to go to very many layers. If my memory is correct, you're only talking about, for most of our models, 3 or 4 or 5 layers. In the chemistry applications we're doing, it just doesn't seem to require many layers. What the layers do is they basically take this wealth of information you feed it initially and find a way to filter it down into just the most important pieces and then correlate that information with an output like interaction energy or whatnot. And exactly how this works is slightly mysterious to me, since I'm not an expert on the computer science side of that. But it's really fabulous that the techniques that the computer scientists have developed are widely available. And all the neural network training, my students write a little bit of code in TensorFlow or other packages, but really it doesn't take a giant amount of work to create one of these models on the neural network side. That part's kind of the easy part. You just pick up TensorFlow or whatever your favorite software packages, and we write a little code, but not months and months of coding. And the hard part is figuring out what data to feed it and how to encode it. And there we can use our expertise as chemists.
Thank you very much. Maybe the last question from Dr. Janjua again.
Yeah, thank you. Thank you, Professor Nahid. I'm sorry, Professor Sherrill, to bother you again. I have just one query regarding your neural network. How many nodes are there in the first layer? or you can say the input layer? And is it fully connected neural network?
Good question. Yes, we are using fully connected neural networks. That first layer, I'm trying to remember for some of these applications, it's on the order of about 100 nodes, in the ballpark of 100. I think in our initial work, we might have had a node for every symmetry function. I think we had maybe around 100 symmetry functions. I'm not seeing the slide with that info on it right now, but something like 100 in the initial layer. And I think for that one, it maybe stays 100 at each layer until you finally have the output layer, and then you just get one number out.
Okay. Thank you. There was one hand raised by one our ladies. I think now she put it down. If she is available, Asma Yamani, you raise your hand. Are you there?
Yes. Yes. Hi.
Okay.
I didn't personally. I'm a computer scientist major, and I was interested in if you ever tried one of the explainability models, such as Lime or SAPT, that would tell you why is the model making its predictions, and then you can align it with the science that you have and see if is making the same reasoning.
That's a great question. No, I haven't tried the explainability model, so I don't know what would come out of that. I think that's a great idea. We should definitely do that. We have played around a little bit with uncertainty quantification to try to help us better understand if we have a new chemical situation that we haven't trained on, and then maybe we need to go back and mess with our training again. But in terms of the explainability models, we haven't really tried that yet.
Okay. Thank you very much. Now, the last, where is Asim? I was trying to unmute him. Where is Asim? Asim, are you there?
Hi, Dr. Nahed, how are you?
Good. Any question you have to Dr. Sherrill?
No, I'll meet him in a few minutes.
Any question you have to us?
No, I like to thank you. I mean, thank the department
No,
because
actually,
they facilitated this nice presentation, and I like to thank Dr. Sherrill for his good mentorship and for his contribution.
okay.
I would like to thank Asim for all his hard work and great results on these papers that we have under review right now.
And thank you very much, Asim, also for your contribution. And I just, those who are listening, Asim is our student. He's doing PhD under the supervision of Professor Sherrill. By this, our webinar coming to an end, and Dr. Sherrill, you've done excellent job. People are very happy, and you can see the questions. We may continue more, but I think we are getting late here. So we have the recording, and we are going to share the recording on our website, and people are going to look at it, and maybe some of the people may approach you for the work as someone sent me the message. So thank you once again for your time. It was a wonderful talk, very well received. Thank you once again.
Thank you very much for the invitation. I enjoyed talking with you all. Okay, yes, and in fact, I've got another meeting, so I'll sign off here. Thank you again.
Thank you, Dr. Sherrill. Thank you very much. This is Khalid from Chemistry Department.
Thank you very much.
Well, Dr. Sherrill, he is our chairman, and he told me that don't introduce me, but he introduced himself. So he's our chairman. He interacted with you actually.
Thank you for setting up this seminar series. I think this is a great idea.
I'm looking to meet you soon for another seminar in the future, hopefully.
That would be wonderful.
Thank you. Bye-bye.
All right. Thanks, everyone.
Okay.
I'll sign
Thank
off
you.
here.
Thank you. It's a pleasure.